My name is Alex Buckman. I'm the practice manager for networks and energy storage at the Catapult in the infrastructure and engineering team. We've got a double dose of me today. First of all, I'm going to be talking about technologies, and then I'll be talking about infrastructure. So next slide, please, Anna. So the way that I'm going to approach this is, first of all, I'm going to talk about what we saw within the concept design projects and how they approach technologies. So across all of the projects, there were 42 separate technologies that were proposed to be included in these smart local energy systems, and these were aggregated for this chart into 21 categories. So what this is really showing is the breadth of interpretation of scope for what a smart local energy system is, and that will depend upon whether the partners that are developing that concept, and also depends on the natural assets that you have in that area, or potentially those assets that you have existing within homes and within the industries in the area. But we did see some trends that we could pull out. So smart local energy systems will tend to focus on balancing and trading internally between consumers and producers, but they'll also often try to balance or trade between their system and the wider energy network. And for that, you need some sort of control centre, often referred to by smart local energy systems as platforms, and essentially it's the brain behind a lot of the control of your assets. And each smart local energy system concept included some form of this technology. Another theme that we saw is that alongside this flexibility, electric vehicles were mentioned by pretty much all of the concepts, but within EVs there's also a range of different technologies and how they approach them. Some were simply recognizing that electric vehicles are going to happen, and that's going to place certain demands on the system that need to be dealt with. But whereas others would look towards smart managed charging of electric vehicles, or even vehicles to grid, in order to manage the balancing on the system. With smart local energy systems focusing on flexibility, often in order to deliver value, storage was widely recognised as important as well, with most projects proposing new storage technologies as part of the plan, and those can vary anything from behind the meter batteries to the use of aquifer storage. In general, the concepts fell into two broad categories. One was more kind of the broad and long-term strategies, which suggested a range of possible paths and technologies that could be approached in a given area. And the other style of concept that we saw was focusing generally on a shorter time frame, or a smaller geographical area, or a smaller set of buildings, say, but to prove and to do a deeper dive on a particular technology, a particular smart technology, for example, around peer-to-peer trading. So what I would say is that neither is right or wrong, but again, it demonstrated the range of interpretations that the smart local energy system concepts had on the definition of scope. So next slide, please. So we at the Catapult, we do a lot of work that can support smart local energy systems, and when you set out to develop a smart local energy system, you want to understand what you have. So one of the objectives set by the PFER programme to challenge smart local energy systems is to provide world-leading customer experience, whilst also improving infrastructure productivity and reducing consumer bills. And so to do this, you really got to understand whether you can leverage any of your existing assets to achieve that. And so you want to understand who your consumers are, who your customers are, what types of homes do they live in, and what are the commercial building energy consumption characteristics, how much fuel poverty is there, and also you want to understand what assets are already in the area, and for example, how much embedded generation there is, how many kind of hot water tanks are in homes, things like that. And so one thing that the Catapult's been doing throughout the PFER programme is providing local energy asset representation reports to each of the smart local energy systems in the PFER programme. So the project concepts and demonstrators have generally described their local energy asset representation reports as interesting and helpful. They have reported using the ELIA results and data to complement and support their modelling. The next slide, please. So In general, it's the exception, not the norm, to see a SLES design that aims to island itself in the wider energy system. It's unlikely to benefit the local or the national energy system to do so, albeit there are certain circumstances where you might see it happening more so. And when we're looking across the concept SLES design, discuss their integration with the wider energy system. One of the primary reasons to do so from a SLES perspective is to access revenue streams. By investing in flexible technologies through infrastructure, SLES can access assets that were previously difficult to control to both the benefit of the wider and the local energy system. So we have a lot of distributed assets, everything from behind the meter storage, the thermal capacity of building materials, through to your local resources, distributed technologies that are really hard to control at a national level, but at a local level it's much easier. Well, if SLES are developed. Given the early stage of the concept designs, there was not much detailed analysis into the revenue streams being developed. However, most of the concept designs specified revenue streams from either energy system services or forms of energy arbitrage. It's challenging to know how these technologies will perform under future wider energy systems without which have substantial uncertainty, with risks of potentially dwindling revenue income, stranded assets and sunk costs. So one thing that we can do within the Catapult is use our whole energy system models to explore what least cost energy systems look like and how uncertainties impact upon their design and operation. In particular, one of our latest models, the storage and flexibility model, focuses on the role of storage and flexibility, as the name suggests. We take a market and policy agnostic techno-economic approach and design net zero energy systems that meet end user demands with the least investment and operational costs. There's a report that's on the screen there called Balancing Supply and Demand that gives a bit more of information on it. And as part of this, we look at the need for system services, which will vary based upon the penetration of intermittent generation and high inertia, low flexibility technologies such as nuclear. So it has understanding the role of flexibility within future energy systems enables the design and development of smart local energy systems that have resilient value streams. So moving on to the next slide. So whether an islanded network or an integrated one with a wider energy system, it's important for smart local energy systems to be able to understand how the technologies invested in will perform under different local or national market conditions, both in the short term and in the long term, accounting for that substantial uncertainty. So in the near term, we want to understand how technology or a set of revenues will perform given the operational characteristics or of other assets in the local energy system. And one of the tools that we have to explore this is dynamic energy system simulation, which uses computational tools to simulate operation of flexibility and responsive demand, allowing smart local energy system developers to study potential business models from both a commercial and a physical point of view. We represent actors' decision-making amongst options available within the market, policy and regulatory frameworks, digital infrastructure capabilities and physical properties of underlying energy system components. For example, the chart on the left of this slide shows the dispatch of a battery against time-varying price signals, and not shown are the site demand and PV generation, which also affected the dispatch. When we look over the longer term, as the wider energy system changes, the role of those technologies may change, and the storage and flexibility modeling capability that I just described helps to understand how the role of those technologies can change over time. So this chart that we see here shows in one particular scenario the duty cycles of a range of storage technologies in 2030, but equally we might want to explore the most cost-efficient use of managed charging in vehicles out to 2050, so or any kind of flexibility. So it's useful context to place the design of your smart local energy system within.
42 technologies were included. Is there a definitive list of those technologies and or the providers that made the cut? And I had an addendum added to that privately, which just said the asker was trying to get a feel for the overlap with ESC's digital energy landscape infographic. Alex, what are your thoughts?
So we do have a list of those 42 technologies. They are So the 21 technologies are going to be listed in the report that's going to be released, and the 42 we've got listed privately. I imagine that if you got in touch with us offline, then we might be able to give you some more information on that. We won't be able to give you the providers of all the technologies, and that's for two reasons. One, because these concept designs weren't always identifying the providers of those technologies because they're quite early stage. And two, if you wanted to get a better idea of the types of technologies that are being used, you might want to look towards the project participants within the Smart Local Energy Systems to get some idea of who the providers might be.